So today is a continuation of videos that I'd started in part 1. We're going to talk about molecules in the solid state. And in particular, we're going to talk about molecules that are in crystalline structure, not amorphous structures. But if you look at crystal structures, whether they're created by ions or it's molecules that connect by some sort of weak intermolecular bonding or polymers that all connect through strong covalent bonding, or maybe these are even complete molecules like proteins that pack together in some sort of crystalline structure. To understand those, we usually analyze what we call the unit cell, and basically that is just the first repeating unit within this crystal composed of numerous molecules. And this particular unit cell is defined by what we call lattice points, which are the four corners that we pick out. And these lattice points might represent the center of an atom, an ion, a molecule, or as I described earlier, even a macromolecule. So what is a unit cell? Basically, what's the criteria? And to understand this, we're going to just look at a checkerboard. We're going to talk about something in 2 dimensions to try and just wrap our head around what's going on in 3 dimensions for a unit cell. So if you looked at this checkerboard and you were trying to pick out a unit cell, which I have blocked out in yellow here, is that the unit cell is the simplest repeating unit in the crystal. Opposite faces of the unit cell are parallel. So this particular face is parallel to this face. Every lattice point has similar surroundings. So if I was at this lattice point, I'd have no way of knowing if I was molecular size that it was different than this lattice point, because the surroundings are relative to a red block in the center and surrounded by 4 blacks that would all appear the same. The edge of the unit cell connects equivalent lattice points. So once again, we've described these lattice points as being equivalent. The connection creates an edge. And of all the crystalline materials we found in nature, they can be categorized in these 14 what they call Bravais lattice groups. And in general chemistry too, we really are going to only focus on one to understand some of the general principles and things you can do with the unit cell. And that grouping is called the cubic lattice structure. And every one of these is differentiated by both the lengths of the edges and the angles between the edges. Another component that is used to differentiate lattices is symmetry, which can involve planes of reflection or even movements. And crystallographers are able to use these to further define different lattice groups. And this is covered more thoroughly in advanced classes such as inorganic chemistry or materials science. I just want to remind you once again that every one of these is a lattice point, but when they're really filled with atoms, the atoms occupy the entire space of the unit cell. So for example, this cubic structure could be something that crystallizes in a cubic configuration. One of the few atoms we know that does that is polonium. So of the cubic structures, there's the simple, as we just described, atoms on each of the 8 lattice points. The body center cubic, once again, atoms on each of the 8 corner points, but one also in the center. And then the face-centered cubic, atoms on each of the 8 corners, but also a face or a half atom on each one of the 6 faces. And when we look to do calculations off of these cubic crystals, then what we basically will do, and the best model to really look at is the space filling models right here in the middle. So things to glean from a unit cell. One thing is how many atoms are in a unit cell. To understand that, it's good to understand how to read a space filling model. If an atom is in the corner, there's really 1/8 of an atom in every corner. If there is an atom in the face, as there is over here, there's really 1/2 of an atom in every face. And then if there's one in the body, the entire body is an atom. Well, of course, that's one entire atom. The one that isn't demonstrated on here is if you have one along the edge. If you have an atom that's basically centered along an edge, that would represent 1/4 of an atom. And we'll see that example later. So with that in mind, I have 8 atoms at 1/8 apiece. That gives me 1 atom. Here I have the same thing, 8 corners, 1/8 apiece. That's 1 atom, and then 1 in the center. That's 2 atoms in the body-centered structure. This is the most efficient packing scheme of the cubic family. So you have 1/8 in each of the corners. That's 1 atom. And then you have 1/2 on each of the faces, and there's 6 faces. So that's 3. plus 1, that's 4 atoms per cell. The coordination number is how many atoms are around each of the individual atoms. So for example, this is a real easy one to see. If you basically looked at this particular atom, it is equally spaced from every atom that extends out from each corner. So this has a coordination number that's 8. But if you go back here, now that you understand that concept, you could take this atom in the top corner and realize equidistant from that atom, there's at least 1, 2. Now this one straight across on the diagonal is a little farther out, so that isn't considered one of the coordinating atoms. 3, 1 on the backside. If this is the z-axis, then there's one above it on the z-axis. 1 extended out and then 1 extended the other way. So that's a total of 6 atoms around this guy. And if we were to work our way around this guy, maybe starting from this particular atom, you can consider every one of these atoms here along the lattice corners and also the faces. Each one of those are touching this atom. They're the same distance away. So that's 4 from the center, 4 on each of the lattice points. And then if you come out in space, in front, there would be another 4. That's a total of 12. So one of the things I wanted to show you is just a mathematical relationship. You can look at the atoms per cell, 1, 2, 4. Look at that pattern. The coordination is actually increasing in a set amount as well. So basically you're looking at a straight line equation. If you graphed atoms per cell to the coordination number, you would see that it basically is a straight line, and we know that we can establish a pattern of y equals mx plus b, which says whatever's on the y-axis, the coordination number, equals the slope, which is m, times the number of atoms plus b. So we can find this mathematical relationship. So all we've got to do is use our slope formulas here. The slope, just like the slope of a roof here, is found by dividing the change in y by the change in x, or going back to our roof example, is found by dividing rise by run. From here to here, that's 12 to 8, that's a change of 4, and that change by 2 points x. So 4 divided by 2, that gives me 2. So the slope is actually 2 over 1, or 2. And then we can take any of these coordinate points, atoms and coordination number, plug it in here, and solve for the b. So we're going to take this first set of coordinates. 1 atoms will give you a coordination number of 6. Plug that in. B is 4. If you solve for this, b is 4. And that would have worked with either of these other 2 sets. So basically what you have is the coordination number is twice the number of atoms plus 4. And so this is an easier pattern just to remember this by. 2 times 1 is 2, plus 4 is 6. 2 times 2 is 4, plus 4 is 8. 4 times 2 is 8, plus 4 is 12. So that's the mnemonic to remember this. Okay, species radius. This is relative to the length. Now, once again, I want to remind you the importance of this. If I know the radius of this actual atom, that's actually the atomic radius, the covalent radius, or if it's an ion, it's the ionic radius. These are the things that control a lot of calculations in chemistry, as far as the energy that binds them together, what kind of density the material might have, what kind of void space it might have. There's just a lot you can do from this particular measurement. But we can't measure the radius directly, but we can find this in a crystalline pattern. And remember from video number 1, we can determine the length of the unit cell. That can be done with X-ray diffraction. So now the question is, how does the radius of the atom relate to the unit cell? So let's do the first one. Let's compare the length of the unit cell to the radius of the atom. It's pretty obvious that the radius is half length. So if you rearrange that and solve for r, basically L divided by 2 is r. This shape is a little more complicated, so I'm just going to break this out and solve this one. So again, if you take a unit cell length and you're going to compare it to the radius, but now we got to get radius that are connecting from end to end. So if you take a lattice point here on the front left corner and you go to the back side on the right, you'll go completely through radii, getting from one lattice to the other. So that's one radius. You get through this center ball or center atom, that's 2 radii. And then you do this last corner lattice point, and that's another radius. That's 4 radii in there. So we're getting a little closer. Let's put in this blue line, which really is from this lattice point along one face to the other lattice point. It's basically the diagonal. Well, the nice thing is that blue diagonal is related to L, right? These lengths are all the same. It's a cube. So this L and this L are related to that blue hypotenuse according to Pythagorean's theorem, which says L squared plus L squared is the blue line squared. So let's basically just solve for the blue line in terms of L. That's 2L squared. You take the square root of that, the L squared will come out. And you basically know now that the blue line is L times the square root of 2. Now we can express radius in terms of L. Because once again, now we have a right triangle. It's turned a little on its side, but it's still a right triangle. Use Pythagoreans again, set this up where this leg squared and this leg squared added together equals the hypotenuse squared. Start simplifying down. 2L squared would come out of here, plus L squared, that's 3L squared equals 4R squared. If you square this side, you get 16R squared. Now we're going to just solve for R by dividing by 16 and taking the square root of both sides of the equation. Now I just simplify terms. I get that the radius is equal to L times the square root of 3 divided by 4. Now let's go to the face center cubic. Use this exact sort of logic. Here's my L. This time the radius runs along the face. Still, though, 4R, but along the face this time, so the calculation's a little simpler. Because this other leg over here is also L. Pythagorean's theorem, once again. Simplify down a little bit. 16R squared. This equals 2L squared. Just take the root of both sides. 4R equals L square roots of 2. Divide over by 4. And you solve that R equals L times the square root of 2 over 4. So now we have all these relationships. How the radius is relative to unit cell length, which you can find with X-ray diffraction. And then last but not least is packing efficiency. And once again, I want to just show you the proof for this. It's another nice little piece of mathematics. And packing efficiency is basically saying, of this unit cell, what percentage of it is atom versus open space. So here's the stuff we know. This is going to just use a simple cubic cell to understand this. So the total cell volume is L cubed. That's just the volume of a cube. The total volume occupied by an atom is, first off, there's one atom in here. We know that. The formula for an atom is 4/3 pi r cubed. That'll give you the volume of an atom times the number of atoms is 1. So that, or 4 pi r cubed divided by 3. So we want to express R in terms of L over 2 because that's the relationship we have for a basic cube configuration. So we substitute that back in. We clean things up a little bit and we divide this, which is the volume of the atoms, by the total volume. And we basically, as you simplify this down, you're going to end up with the L cubed divided by L cubed, so that'll fall out. This is going to be 2 cubed, which is 8, times 3, which is 24. So 4 pi over 24, if you do that math, is 0.524, which if you express that as a percent, move the decimal over twice, it's 52.4%. So of a unit cell volume, once again, we can find that because the X-ray diffraction will give us this length. We cube it up and we're going to actually have the volume. And we now know that if it's in a basic cubic configuration, 52.4% of that total volume is actually attributed to atom. The rest is open space. And this can help us if we're going to use this material to trap a gas or to trap a fluid, something like that. That'll tell you how much open space is available in there. I'm not going to do the derivatives for these two, but they follow the same kind of logic. This might be something you want to do in your own time, just a good practice. We know this one came out about 52%. When you check this, hopefully it'll come out around 68%. And this one is the most efficient, it's the most highly packed. It's 74% atom. So roughly 25% void space. So how do you use this information if you're given problems? So if we had X-ray diffraction And it's copper. We find out it's face-centered unit cell, so it's this sort of configuration. And we have a unit cell length of 362 picometers. So how many copper atoms are in a unit cell? What's the coordination number? What's the molecular radius? What's the density of copper? And what's the void space in every cubic meter of copper? So these kind of things we can answer from this X-ray diffraction information. Well, the first one's easy. Because of the fact that it's a face-centered unit cell, there are 4 atoms in every unit cell. What's the coordination number around copper in that cell? That's 12. So for every copper, there's 12 coppers around it. And this may be more pertinent for other types of structures if you want to know what it's bound to. Okay, what's the molecular radius of copper? So once again, we know from the length, which we can get from the diffraction numbers, we just plug into this formula and solve for R. And we got 128 picometers. And this, once again, is the covalent radius. It really is the how far the protons reach out to the electrons. And once again, that's important in atoms. You may not want the diameter, you want the radius, because in the center of every atom is the positive nucleus. And out on the periphery, the end of the radius is where the electrons are found, the valence electrons. Okay, what's the density of copper? In every unit cell of copper, there's a mass determined by the atoms present, which in this case, there's 4 atoms present. So if we took the 4 atoms times the molecular weight from the periodic table, 63.55 grams per mole, and then we use Avogadro's number, which says how many atoms are in a mole. You basically are able to cancel out atoms, moles, and you're left with grams. Now, if you take this number of grams and divide it by the total volume, it's mass, by total volume should be density. And one last conversion we're going to make is just to get it back into grams per cubic centimeter, which is how density is usually converted, is we're going to put this general conversion unit in there, factor 1e to the 30th picometers cubed per centimeters cubed. Do this calculation, you get 8.90 grams per cubic centimeter, or 8.90 grams per mil. And this is fairly close to the density you'd find in the handbook for copper. Okay, what's the void space in every cubic meter of copper? Well, this is actually not too complicated. If the 74% of the unit cell is basically full of atom, then the remainder, right, the 26 cubic meters, 26% of that should be void space. So if you basically were talking about a cubic meter, you basically could take 0.26 cubic meters and use that to trap air or to fill it with fluid. So the final set you should know with unit cells is you should be able to look at these things and figure out the empirical formulas if you have the unit cell information in front of you. So I'm going to look at sodium chloride, since we all know the empirical formula for that, and see how you derive that. And my advice when you're looking at these sort of things, if you want to figure out the empirical formula, is basically just count atoms in one unit cell. So remember this information: there's 1/8 of an atom per corner, 1/2 of an atom per face, 1/4 of an atom per edge, and 1 atom if there's 1 atom in the center body, which in this case for sodium chloride, if you look, there's a sodium atom trapped in the center of the unit cell. And that's not as obvious by looking. All right, so sodium ions, 12 edges, right, times 1/4 atom per edge, plus the one that's in the center. That's going to give me 4 atoms. Chlorine ions, if you look at these, there's 8 corners times 1/8 apiece, 6 faces, that's times 1/2 apiece. You add this together, you get 4. So it's the empirical expression is 4 sodiums to 4 chlorines, which is 1 to 1. And remember, ionic compounds are always expressed as empirical formulas. So I hope this has helped you understand a little bit more about molecular solids.